All right, guys, I hope you enjoyed day one. Today is day two of the 100 Days of LeetCode. So without further ado, let's get right to our problem. All right, so this is problem number 50, and upon first glance, it seems fairly straightforward. So let's see if it is. And essentially, we just need to implement the POW function, so the exponent function, which calculates x raised to the power n, i.e. x to the n. Here are a few example inputs and outputs. You can even have negative exponents, which of course will result in a decimal amount or a fraction. And these are the constraints. So we're going to have a number between negative 100 and 100 as our base. And we're going to have, a pretty wide range of potential exponent values. So between negative 2 raised to 31, less than or equal to n, and then 2 raised to 31 minus 1. But we are guaranteed that our x to the n will be between, what's that, negative 10,000 and 10,000. All right, so let's do it. Now, upon first glance, you might just think that the solution to this would be to use an iterative approach. And let's see what happens if we do. So we could do something like double original equals x. All right, so we're basically saving our x value because once we get into our loop here, we need to do n minus 1 because if not, we're sort of we're multiplying when we're at number 1, which we shouldn't be when it comes to exponents. So that's why we do I less than n minus 1, and then we're going to increment I, and then we're simply going to do x multiplied equal to original. All right, now let's see what happens when we try and submit that. It's taking a while. That's the first thing. Okay, so the first thing we see is that we forgot to change this function so that it can handle negative values. And you think, okay, that's pretty easy, because what you can do is you can just say if n is less than 0. Now, essentially, all we're going to do is basically just return my POW x to the negative n, and we're going to return that as the denominator. All right, so, fixed. Should work, right? Again, it's taking a while. And you can see that doesn't work. And the reason why that doesn't work is because we forgot to say if n equals 0, then we are always returning 1. It's one of the rules of exponents. If the exponent is 0, you always have 1. That's always your answer, no matter what. Okay, so now we think, we've probably figured everything out. It should work, right? And you're looking at it, you think, the logic makes sense. So let's see. And we get hit with the time limit exceeded. And what we don't realize is that this way of solving this problem is actually terribly inefficient, and there's a better way to do it. And what we're going to be doing today is something called binary exponentiation, and I've linked that in the description below, a really good explanation of what that is. I'll explain it a little bit when we're implementing it, but if you want to read that, and if you're into something a little more mathematical, you can check out that link in the description. All right, so let's scrap this. Okay, so when we implemented that, first thing we saw is that we need to have some checks, right? So we need to say if n equals 0, we're going to return 1, all right? Because now this function is not going to be iterative, it's going to be recursive. And we say else if n equals 1, you can simply just return x. Oops. All right, so we got 0, we got 1. Now let's do sort of the crux of the matter here. So what we're going to be checking now is if this number is an even number, the exponent, right? What we can simply do, and this is explained in the link that I've left in the description, is we can simply say, okay, instead of thinking about it as x to the power of n, we can think about it as x times x to the power of n over 2. All right. So now, instead of doing, for example, 4 to the 10, we can think of that as 8 to the 5. So what it does is it essentially will basically reduce the amount of computations that we need to do a lot quicker than if we were to use the iterative approach. So now we're going to end up doing log n operations as opposed to n, which is a lot faster, and you're not going to get this whole time limit exceeded situation over here. Okay, so that's great if we have an even numbered exponent. But what if we have an odd number? So we get something like that, right? What do we do here? Well, now what we want to do is we simply want to say, pretty similar to what we had above us, but because we're doing n minus 1 divided by 2, we do have to multiply it by x one more time, and that's what we're doing right there. Okay. Now, the last thing we forgot is we need to check for negative exponents, and that can simply just be in the else statement. We're just going to do return my pow with x, and then it's going to be negative n now. And again, oops, forgot. It's going to be 1 over that. All right. And we can just say at the bottom, return 0, which we don't even need. Let's see if this works. Of course, because we simply put that in brackets and we didn't call the actual recursive function. There we go. So we can see now we have a very quick solution to this problem. And it's actually cool because it shows how something that at first glance can appear, very easy. You actually have to think about it a little bit if you want to come up with something a little more efficient. It's kind of like the Fibonacci solution, the trivial and the naive, or I should say the naive solution to the Fibonacci, that'll break your computer. But then if you come up with something using, the memoization solution, you'll have something that's a lot quicker, more efficient, and, your $2,000 MacBook doesn't set on fire, so that's always good. But yeah, we've solved this problem. Thanks for watching, guys. On to day 3.